Okay. Make the thing focus. Focus. Still doesn't want to focus. There it is. Okay. This is a situation we did in lab. And still kind of set up with there are a lot of things disconnected. Pinch gradients just need electric field, which is the potential by the change of potential by the distance. Since it's constant. If you had a non-uniform wire, you wouldn't have a constant potential gradient. You'd have to have the same current throughout the wire, so the potential gradient with wires, let's say tapering, potential gradient would have to change, have to be greater than the wire is narrow. Because you need more electric field to get the same amount of current, same amount of charge drift through the part of the wire, and that's something you probably ought to make note of and think. Okay, so there's potential gradient. Okay, well, we're trying to find how many amps. You know what the potential gradient is? You've got this distance, you've got these two resistors. Assume the ammeter, well, this is the ammeter resistance. So assume that there's no resistance at all. Okay. Okay, so I'm not sure. Should have really had to use that in. That's fundamental. So make sure you focus on that idea. But once you have that, let's go get came up with a good result here. Okay, so what's the result? Well, let's call this point here C. Call this point D. So I can just have the notation. Then the potential C to D is its potential gradient times delta X. Now, you want to think in terms of proportionality. When you have a constant potential gradient, you can do that, but more generally, this is going to be the case. Okay. And actually, if you had a changing potential gradient, you have to integrate the potential gradient with respect to X. Make sure you understand that. But in this case, everything's simple. In a potential gradient is just going to be potential rate of B times delta X over L. Because if you multiply VAB over L by delta X, which is the same thing, if you want to think of it that way, is multiply VAB by delta X over L, you want to be careful about that. So we come back to the potential gradient, and we have this. Okay, well now we have a simple series circuits. If you know what to do with series circuits, that's great. But we're not going to do this using formulas for series circuits, because we're starting chapter 46, and you don't even know what the formula is, even though you do. And we want to do it for basic principle. So now the principle is from this point to this point, we have this much potential change. Okay, the potential drops from here to here, assuming the VAB is positive. Right? And if VAB happens to be negative, well, When the negative drops, it becomes positive. Whatever, the potential here changes from here to here. Which means that it changes if you go along this path. Okay, so let's say. Let's just call this point E. Point so along the path CD or along the path CED, I just put E down here somewhere, you know. Okay. And it's also handy because now we're talking about potential drop from C to E and a potential drop from E to D. Now, when we get up to point C, we have some current. Then we have a current, let's call it I here. Then a little bit complicated, but we have some current going down this way. And some current going this way. And some current coming back this way. And some current going out this way. Well, let's just call these currents. Let's call this current I1. Let's call this current I2. Let's call this current I3. And this current here has got to be I. Now, what actually happens is you have a little less current between them, which actually means you have a little less voltage drop than what we're saying. Okay. So we need to make an assumption here, the assumption being that we're not pulling much current. Okay. So current I equals I1 plus I3. Because there's no place for charge to build up. If you got a tenth of an amp running along here, in 10 seconds, you got a whole coulomb of charge running by here. If it starts building up, you better get out of the building. Okay, that's a usually you're gonna have light. You know, that doesn't happen. Now, if you got a capacitor, you can store charge, as you know. And silent capacitors. And we'll throw capacitors into these things. Actually, kind of soon, like next time. Okay. I1's a whole lot less than I, and I3 is pretty close to I. So assumption of constant potential gradient valid. To the extent that I want is a whole lot less than I. So if you got a significant amount of resistance here, got enough resistance there, it prevents a whole lot of current from being pulled off and changing this potential gradient. And of course, I2 is equal to I1 because current's got no place to go except back up here, right? So I2 equals I1. Because you've got, all this stuff. That's the ammeter. You know, resistance here. Okay. Current has no place to go. It's always the same throughout. All right. In this case, it's valid status. If there's too much current here, then the voltage between C and D, it actually is a little bit less than what you get from this. Because this is based on constant potential gradient. So the constant potential gradient along this wire here, again, is based on the idea that we're not tapping off the whole lot. And what we did, you know, we're getting a 50 microamp current, 30 microamp, 40 microamp. So whereas we had more like 100,000 microamps running through the circuit, running through the line. Okay. So 30 or 40 microamps will pose 100,000 microamps. We were pulling just a small amount of current. All right. Now we can just look at this part of the circuit. I want a bigger picture of that. With this. Now we have voltage VCD between this point and this point. This creates a flow of charge because all these things are conductors. The resistor might be a pretty bad conductor, but it's no conductor. Got some voltage across the ammeter. We have some voltage. Resistance. So what is the expression? The voltage across the ammeter and the voltage across resistance. Well, we got current. It's all kind of introduced this again. We got I going. Got I. We're call it I will. I want to still flowing here. And then we've got current I here, and a current I3. So my loop looks like this. Do it like this. So I1 is flowing around this loop. Not flowing around the loop, it's something else. So it's over here. It's voltage. Voltage across A is I1 times the resistance A. Voltage across R is I2 times the resistance R. Now the potential change as you go from here to here has to be VCD, right? And the potential change here is this, and the potential change here is this. So the voltage C to D. This voltage cross A plus voltage cross R. So now what's the voltage from C to D? Well, I'm going to call that I1 times R equivalent. R equivalent being the equivalent voltage of this and this. That's the equivalent resistance of this resistance, and this resistance, and this resistance. If you just put this in a black box and put an ammeter here and a voltmeter here, then you're going to get a current and a resistance. I'm sorry, you're going to get a current and a voltage. You're going to have a current and a voltage. And a current and a voltage give you resistance. So that here resistance is out. Now, in general, resistance in theory out. Well, what we're looking at is a loop and currents. And I've really talked about the ideas behind Kirchhoff's law. And Kirchhoff's laws is what your homework starts with. Well, let's talk about in general context. Not just about the context. So, so here are Kirchhoff's laws. Okay. Just all this. The way we want to write one of Kirchhoff's laws, I think it's probably the second, but first law, second. Okay. Second, I think that's with currents. First with voltages, we put on this. Okay. This is called a branch point. Okay. Well, put in the branch point of zero. Current can't accumulate. The branch point. We accumulate a capacitor, but this isn't a capacitor. In this case, I'm going to say that I1 minus I2 minus I3 is zero. And the total voltage drop around the loop is zero. What's that? That's conservation of energy. Energy conservation, why? Since electric field is conservative. Half independent. So if I have current I1 here, and I3 here, and I here, and I here. Well, around this loop, all this R1, R2, and R3. And just for good measure, let's go ahead and put a resistor in here. We didn't have one, but it was not assuming. This will be resistance R4. Now we've got a loop. Here around to here. If we go around this loop in the counterclockwise direction, What's the voltage drop here? What's the voltage drop here? What's the voltage drop here? And what's the voltage drop here? Well, current here, here, and here is I1. These are the voltage drops. We call them delta V1. Delta V2. But, well, what's V1? The voltage drop in the direction of the current. Voltage has to drop to get a current over here. The voltage here drops by I1 R1. So current continues around here. It drops across R2. If relative to this direction, and we could have a loop running in this direction if we wanted to. And then these be our direction around the loop. Yeah, I think those pictures, I'll say that, I'll say this again. Now, we're going to run the loop in this direction. But now we've got a current in this direction, which is opposite the direction around the loop. So going around the loop, well, the current has to drop from here to here. We're going this way around the loop. We're going in the direction opposite that of the voltage drop. In the direction opposite the voltage drops, our voltage change, our voltage drops on the beat. Minus I3. And I don't know what I put I1, I2, I3. Maybe that's the reason you look at it like I'm nuts, which is probably true. Okay. It's I1 here, I1 here, and I1 here. Okay. So that's how we would write. All the voltage drop around the loop. Now let's make this line. So let's say I've got current. Well, let's just say I've got a network of this is like so. I have a current I going in here, a current I going there. And then just make it fun. We've got resistance across here. Yeah. And then here. And here. Now let's say we put the source here. I'm going to analyze that circuit. Well, let's put some subscripts to these. Analyze this circuit. You got to say, well, let's see. I've got some current I1. I've got another current I2 here. Not equal to I1 anymore because current's branching off here and here. All kinds of things. Then I've got a current I3 here. I4 here. What am I gonna do about that? Well, I'm gonna start writing equations. I've got 4 different currents, and actually, you know, I'm gonna have an I5 here. And start writing equations. Got 5 unknowns, 5 different currents. So I'm gonna need 5 equations so I can solve them. They're gonna be linear equations, which ought to make you happy. Remember linear algebra. You know, I put them in a matrix and solve them, okay? There are many ways you can solve it. It turns out, you know, 5 equations and 5 unknowns can seem a little intimidating, but the way they work out, they actually end up. Okay. Okay, so how many branch points we got? We got one here. We got one here. We got one here. Okay. So this branch point, let's label these branch points. Let's label this branch point A. Let's label this one B. Let's label this one C. And this one is D. So we've got 4 branch points. Branch point A, we can say about the current, we can say that I minus I1 minus I5 is 0. Branch point B, we can say that I know the current. Get to the branch when I realized that the current that I didn't label. So B, I have I1 coming in. Then I2, I4 and I6. Careful, I1 coming in, I4 go this way, I6 go this way. Well, write out what we have in C and D. Okay, I think everybody looked like they're doing pretty well. What happens at C? We have I5 coming in, I2 coming in, and I going out. Then it's clear that we have a 40. Okay. At D, we have I6 and I4 coming in. How do I know that I have I4 coming in? I don't see it there. Well, where it has no place to go. I4 is here, it's gotta be here. Okay. We got this. Okay, well, there are only 4 branch points. Now we can do loops. Okay. My loops have to be linearly independent. Meaning, I can have a loop here, this little triangular loop. And I can have this loop here. And triangular loop. If I've got those two loops, I can't have this one. It's really a combination of these two. Makes sense? I can't go A, B, D, C. If I go A, B, C, and B, C, D. Okay. So on the loop, A, B, C, my voltage drops have to get up to 0. So my voltage drop across R1 is I1 R1. Then I'm going to draw a little loopy arrow showing that we're going counterclockwise. My voltage drops according to the way I've drawn I1. My voltage drops from here. Then it drops from here to here. Then I have a negative drop from here to here, just like we did before. So we have I3 R2. And then we have minus I5 R4 equals 0. I'm going to do this loop here. So we'll have a point B. Just like it's a loop VDD. Again, counterclockwise. So I have I4 R5. And then I've got this source. Well, this is positive and this is negative. Okay. So the voltage doesn't drop, it rises from negative to positive, right? So we have then minus all this V sub S, V sub A. That's this loop. And I've got my current I up here. I should have put a subscript for that since these currents all have subscripts. So I'm going to call this I sub 7. We're going to change my I sub 7. Here, here. Well, so far I've only got 6 equations. I've got 7 more nodes. I'm going to assume that DS is okay. What am I going to do? Well, I'm going to pick another loop. We've got lots of loops to choose from. So I could do this whole rectangular loop, right? A, B, D, C. Or I could do just B, D, C, or B, C. Put it right down below. Then I have a big old map. Bunch of simultaneous equations. Well, I'm not gonna show you how to solve simultaneous equations. Showed you last year at this time. Well, before this. And they look really ugly, and these reasons, take a little bit of work to do. Well, just to show you. We want to clean these up a little bit, and we want to leave space for 7 variables. So I'm going to start with the A. Okay, I have negative I1. Then we're going to have minus I5. Plus I7 equals 0. For B, I've got I1. And then I've got minus I4. Minus I6. Equals 0. So you got a lot of spaces in here. We figured you're gonna have a lot of 0 coefficients, so when you set up the matrix, it'll be have a lot of zeros. Probably have more zeros than it has symbols. On C, I'm going to have I2. Plus I5. Minus I7. And look what happens if I add first row, first equation to this equation, I eliminate everything, the I1 and the I2. Okay. So you see that there are a lot of opportunities to simplify these things. Okay, D, we're going to have a negative I2, a positive I6, and I4. That's equal to 0. Then I've got these 2 loops. It's not going to be enough. We need another loop. Got I1 R1. It's like 3 R2. Okay, I'm going to have 3 by the right. I3 R2 minus I5 R4. Equals 0. And then so having written the equation like this, I'll pull a VS over on this side because it's done. Put it like this side, but it doesn't match up with any of the eyes. So keep going here. And then one more equation. Then I can start solving. Now, one thing that people tend to ask in a case like this is, oh, how am I going to know what direction these currents are in? It's getting pretty complicated. I've got this voltage here. This voltage could drive this current back this way. Okay, depending on what else is going on. So I don't know if this is going, I6 is going this way or this way. Doesn't matter. If I choose the wrong direction, when I solve, I'm going to get a negative. Then I know what direction it's in. Okay. Again. We have really very simple principles. Total current into branch point is 0. And total voltage drop around a loop is 0. Conservation of energy and that generator and the sparks that we get from nanocoulomb are don't convince you. Maybe nothing will, maybe make you touch that. Total current in the branch from base to 0. Start accumulating current, which you can get light, or at least sparks. Okay. Not gonna happen. So with those two principles, we can write a whole system of equations that analyzes somewhat complicated now. If we want to put capacitors in here, we can. Then we can start writing differential equations. Because these things could become differential equations. You're ready to change the charge of a capacitor is current and stuff like that. That's pretty much it. Now, a couple of things that are pretty easy to understand. I think we already talked about capacitors. You put them in series, you put them in parallel. Well, we just saw what happens if you put resistors in series. You have the resistance. Well, I'm going to do it once more. The two resistors R1 and R2. Their current I. Same current. What's the equivalent resistance of this? Okay. Well, let's call this point A, let's call this point B. Voltage made of these current times the resistance. Voltage is voltage drop across here, voltage drop across here. It's I times R1 plus I times R2. Well, I divides out. No, if you got resistors in parallel. It's supposed to be R each versus equivalent. That's some voltage made of here, some voltage change to the V. Comes across R1 would be AB. Why is that? Because these wires are assumed to be of zero resistance in the ideal case. Of course, if they aren't, then you gotta worry about that. But it's a low resistivity of copper, for example, copper wires, you don't have much problem with that. Okay. Point is, from here to here, there's no voltage change. And from here to here, there's no voltage change. But the voltage change from here to here has to be VAB. Meaning that the voltage change across the resistance has to be VAB. Okay, and you can just think of it, this is at the same potential this is at the same potential this is. There's no potential drop across it, I do that. So. What else? Okay. Potential across R2. Is VAB. They cannot in general have the same current because you have the same potential drop across two different resistances. So that you have a current I1 here, current I2 here, so that potential drop is I1 R1, it's also I2 R2. Total current I1 plus I2. So that I1 plus I2 times R equivalent equals VAB. Well, R1 is VAB over R1. I2 is VAB over R2. And you multiply that by R equivalent. You get VAB. How VAB divides out, giving you 1 over R1. So you got 1 over R1 plus 1 over R2 plus R equivalent equals 1. So that R equivalent right? And there's your rule, parallel resistance. It's not tremendously helpful when you're looking at network like this, in a simple network, it works. Okay, now you also could be recognizing the similarity between these two rules and the rules for capacitors. But if these were C1 and C2, this would be equivalent capacitance of a parallel. So capacitor. This would be the equivalent capacitor absence of a series, and we talked 2 weeks ago about what that is. Okay. Yeah, if they're in parallel. Well, if they're in series, they have the same charge at both places. If they're in parallel, they have the same potential difference. And you just go from those principles to understand these rules rather than just using these formulas. You want to understand. Just going to be able to use what you know more. Okay.